We had already stepped into the mathematical part of the solid state. In the last video, we had discussed about the packing fraction and the relationship between A and R, that means the age of the unit cell and the radius of the atom. So we had first established the relationship between the age and the radius, that is between A and R. Then we had discovered the packing fraction in the simple cubic lattice. Today we are going to do the same for body-centered cubic as well as face-centered cubic, that means the BCC and FCC structure. It is needless to say that the BCC and FCC structures are comparatively complicated. So let us see by drawing the structure and let us establish the relationship, and we'll see what is the actual packing fraction for them, whether is it more or less compared to the simple cubic. Here I have drawn a prototype of BCC, body-centered cubic. So as we know, just a quick reminder that the atoms are present at the corners. Atoms are present at the corners, and simultaneously there is another atom present at the body center. Same structure in a closed pack structure has been drawn here. I have discussed already what is a closed pack structure on the last day. So same thing has been drawn here. So this is A, this is B, this is C, and this is D. Suppose these are the four corners. Now let us join this line between D and A. Let us join this line. This line I am talking about, the green one. And let us join B and D also. Carefully see. See this triangle. This angle is actually a 90-degree one. So this is a right angle triangle. Here, let us see what are the things that we already know. We know this is the edge, that is A. This one is also A. And see how much is this much. This is R. This is the center. So this is also R. This is also R. And this is also R. Carefully see. This is the radius of this body-centered atom. So this is R. This is also R. This is also R. This part, half of this, and this to this is also R. So we can write from here that it is the AD. It is called body diagonal, which is called body diagonal is equal to, I can write R plus 2R plus R, that is 4R. AB is equal to A, that is the edge. Now, if it is a right angle triangle, for triangle A, B and D, we should be able to write this one AD square is equal to AB square plus, which one? BD square. AB square is already known, that is A square. But what is the value of this BD square? That we don't know. So we should be able to find it out separately. So to do that, check this triangle now. This one, B, C and D. Check this angle. It is a right angle. So here I am writing for triangle B C and D, I should be able to write BD square is equal to, that I am trying to find out actually, should be is equal to BC square plus CD square. Now BC square, that is A square, and CD square, this much is also the edge of the unit cell. So that is 2A square. Now we have got the BD, value of BD square is equal to 2A square. So we are finding it from here itself. So that is 2A square. So it becomes 3A square. AD square is equal to 3A square. So AD immediately becomes root 3 into A, and we have already mentioned that AD is nothing but the body diagonal, which is equal to 4R. So we can say 4R is equal to root 3 into A. So R is equal to root 3 by 4 into A. On the other side, we can also say that A is equal to 4R by root 3. So these are the two necessary equations that we will be using, or you can say that is the relationship between the radius and the edge for the body centered cubic. I hope it is clear by now. Now we are going to find out the packing efficiency of this. So to find it out, packing efficiency, as we know, it is the volume occupied by atoms divided by total volume of unit cell. I have kept this two relationship, it will help us out. So from here, if we see volume occupied by atoms, how many atoms are there? It is 2 into 4 by 3 pi r cube. We are assuming that the atoms which are present, they are spherical in nature, as we have imagined in the last cases also. Total volume of the unit cell. So obviously if the edge is A, total volume will be A cube. Here this relationship will be helpful. How? So I'm just rewriting here. Packing efficiency will be is equal to 8 by 3 pi r cube divided by, now A cube. So quickly you can see here, A cube should be is equal to 64 r cube divided by root 3 into root 3, that is 3 root 3. So here we can write 64 into 100%, of course, into 100%. So it is 64 r cube divided by 3 root 3. Now you can calculate, you can simplify, you can cancel these two out, 3 and 3, that will cancel out. If you calculate, ultimately the value will be close to 68%. That is the packing efficiency of the body centered cubic. So first we have established this relationship, then like the previous case, like last video we had discussed about the packing efficiency of the simple cube. Today you could see it is 2 into this and we are getting 68%, which is greater, remember, compared to the simple cube. We had seen in the case with BCC. Now this is for FCC. We have to understand the FCC structure first. So there are 8 corner atoms and there are face center atoms. You can see on the center of each face there is one atom. I have chosen a particular face, that means this face, this one over here. So this face center atom has been drawn keeping in mind the closed pack structures. and these are closely attached with these two corner atoms. So if it is A, if it is B, and if it is C, obviously this is one edge and this is another edge. Both of them are A and this is also A. Right? Now the point is, if this A and C is attached with this one, this is called face, this is face diagonal. This line, green line. What is the significance of this line? The significance is this much is R, it is the radius of this corner atom. If it is the center, this much is R, carefully see, and this is also R. Here also it is R. So AC, which is the face diagonal, is R plus 2R plus R, which is 4R. And obviously this one is a right angle triangle. So triangle ABC, which is a right angle triangle, for this one, if we see AC, this AC square should be is equal to AB square plus BC square. Now AC square, this much, which is, we will write it down later on, AC square. AB square, let us first write. It is nothing but A square, and BC square is also A square. So it becomes 2A square. So AC becomes root over 2 into A. Now AC, as we have already mentioned, it is nothing but 4R. So from here we can say 4R is equal to root over 2 into A. So R should be root over 2A by 4, or you can say A by, it is, if it is root 2 into A, it will be root 2 into root 2 into 2. So you can cancel this one out, it will be A by 2 root 2. This is one relation. Simultaneously, A can also be written as 2 root 2 into R, and this one we will be using to find out the packing fraction of the FCC structure. So this is the relationship between R and A in case of FCC. You can see we are using this face, we are using the face diagonal. It is comparatively easier, I would say, compared to BCC. We are getting the relationship between A and R. All the relationship between the radius and the edge for this one is for FCC. For BCC, FCC and simple cube are not same. Now, let us find out the packing efficiency for FCC structure. We know the formula. Let us rewrite once again. We are finding out the packing efficiency for FCC. We know that the packing efficiency means it is the volume occupied by atoms divided by total volume of unit cell. And obviously we find it out in terms of percentage. So in FCC structure we have calculated earlier already that the number of unit cell is actually 4. The number of atoms present in a unit cell is 4. We have calculated that. You can see the previous videos for that. Into the volume occupied by each atom, that is 4 by 3 pi r cube, divided by the total volume of unit cell, that is A cube. Now A value is 2 root 2r. So here you can write 16 by 3 pi r cube divided by into 100, of course. A cube means it should be 2 root 2 r whole cube. Sorry. Yes, 2 root 2 r whole cube into 100%. So it is 16 by 3 pi r cube divided by, it will be 8 into 2 root 2 r cube into 100%. So it becomes 16 by 3 pi r cube divided by 16 into root 2 r cube into 100%. For calculation, it is coming out, we can cancel the things out, it is coming out to be 74%. So for FCC, it is almost equal to 74%. So we have got three values. For simple cube, it is 52 around. For BCC, it was 68 around, and here it is 74. So obviously we can see in case of FCC, it is the maximum. That simply means the packing efficiency of FCC is much better compared to BCC or simple cube. That means the atoms are much more closely packed in case of FCC structure. Up next, we are going to find out the density of unit cell. Rather, we should say it is the expression of density of unit cell. Let us see the calculation. For any unit cell, just a simple one. If we consider this much as A, so if we write down like this, density, if we express as rho, so the density of unit cell, or rather density of unit cell should be equal to mass of unit cell divided by volume of unit cell. Obviously mass by volume. Now density we are designating as D or rho, whichever you like. I'm writing as rho. Now mass of unit cell. What should be the mass of a unit cell? We know only at the lattice point the atoms are present. So the mass of the unit cell is nothing but the mass of atoms. So we have to calculate the mass of the atoms. Here we can write mass of all the atoms present in a unit cell divided by the volume. Interestingly, if we want to calculate the mass of a unit cell, which is say M, and if this is V, mass of a unit cell, what it is? It is the number of atoms present in an unit cell into mass of each atom. Now suppose the number of atoms present in a unit cell is say Z, say any number, into mass of each atom. This part can further be expressed as what is the mass of each atom? It is the mass of, or you can say atomic mass divided by Avogadro number, isn't it? Because if we want to calculate the mass of individual atom, we have to see what is the atomic mass of that divided by the Avogadro number, of course. So atomic mass, if we are designating as capital M, and Avogadro number as N or N naught, whichever you like. So here it should be M divided by N0. And volume, if age is A, what should be the volume? It is nothing but A cube. So finally, we have got the value of M, we have got the value of V also. So we should be able to write rho is equal to, which is the density, mass of all the atoms, small m, which we have calculated Z into capital M by N0, Z into capital M divided by N0, this is Avogadro number, mind you, into the volume, that is A cube. So A cube should be here. So this is the formula that we were looking for, and that will be used to solve the various type of numericals.